For our group project, we wanted to explore Benford's law in different bases. Our goal was to find out whether a data set in Benford's law, base 10, would still follow in other bases. You may be asking yourself, what is Benford's law? It deals with the distribution of leading numbers in data sets, where the most common leading number is usually 1. It is followed then by 2 and 3, and so on, with each leading digit occurring less than the previous. This graph recovered from the Information Systems Audit and Control Association.
We started with a small data set with about 15 to 20 numbers. With this data set, we were unable to find a distribution worth creating a graph to accurately represent Benford's law. So, we used census tax data from each state, which contained thousands of numbers, to better represent Benford's law. This gave us a large enough data set to start our investigation of the mathematical phenomena that is Benford's law. With this data, we found that there is an accurate depiction of Benford's law in base 10. From here, we wanted to find out if Benford's law sticks with bases 2 through 9 as well as it did with base 10.
We started by exporting our new census data into a Google spreadsheet so we could work with and manipulate the numbers more easily. We needed to look at the leading digit of all the numbers in order to find our pattern. In Google spreadsheets, we found a way to separate the leading digit away from the rest of the number sequence. This equation represents how to separate the leading digit. Once we separated the leading digits for base 10, we created a graph and compared it to Benford's law's predictions. Even though our graph wasn't exactly what Benford's law showed, the regression line that best fit our data was still very similar to that of Benford's law. At this point, we decided that exploring other bases was worth pursuing. Next, we decided to find an algorithm to convert all the data into bases 2 through 9. The equation to convert is equal base, parentheses, the number you are converting from base 10, which in this case is in column A, comma, the base you want to convert to. In this example, we used base 2. We then were able to take off the leading digit of each number in each base. We were able to use our previously discovered algorithm to separate the leading digits from the number sequences.
Once we were able to change the base of every number in our data set and rip off the leading digit of each term, we summed up the amount of each leading digits for each base. We created pie charts. As you can see, this is not a good way to compare Benford's law, considering Benford's law is a bar graph. However, the nice thing about pie charts is that it is obvious to see that the leading digit is 1, occurs more than the leading digit 2, and so on. We created graphs for each base with the account of each leading digit and decided that this wasn't enough to compare to Benford's law's curves. So, we found the percentage of occurrence for each leading digit, which gave us more similar graphs to Benford's law. Simply eyeing the graphs was not accurate enough in determining the relativity to Benford's law prediction. So, we found the equation for Benford's law in base 10, and then changed it so we could find the predictions for each base.
The equation that we found to predict each digit for each base was log to base b of 1 plus 1 over d. The variable b represents the desired base, and the variable d is the desired leading digit percentage
we found this
were looking
equation
for.
from Wolfrian Math World and deemed it as a reliable source. For example, if we were looking for the percentage occurrence for the leading digit 4 in base 8, this would be the equation.
With this simple equation, we were able to find out the predicted percentage of each leading digit in each base for Benford's law from the known percentages of base 10. With these percentages, we graphed Benford's law's predictions for bases 2 through 9. By comparing these graphs to the graph of base 10, we can see that bases 2 through 9 follow Benford's law pretty closely. We compared the predicted percentages from Benford's law to the actual percentages for each base, and found that each leading digit was close to the predicted value. This method of comparison was effective, yet it was not easily represented, so we found the best fit lines in the equations that went along with each base.
For example, this represents the predicted graph for Benford's law base 7, along with the graph for our data in base 7 as well. This is a good representation of the rest of the data in their graphs.
The equations that we found for each of the graphs. As you can see, these equations appear to be similar, but we wanted to find the exact difference between them, so we determined that the difference between the areas under the curves was the best method. Some of these don't have any difference, and most have a small margin between the two. We found that the average margin between all the bases is 0.0198, which demonstrates that these graphs are very similar. Base 3 had the largest difference of area under the curve, however it was only 0.105, which still isn't a significant margin. This leads us to conclude that across base 2 through 10, our data was able to follow Benford's law's predictions.
We set out to determine what would happen to a dataset that followed Benford's law and was changed into other bases. We found that even in other bases, that dataset would still follow Benford's law. This led us to the conclusion that if a dataset follows Benford's law in base 10, then it will also follow Benford's law in bases 2 through 9 as well. A further exploration into this topic would be exploring bases larger than 10, but we decided that would be difficult to find a Benford's law prediction in bases larger than 10, considering it would be impossible to use logarithmic equations with letters in them, which are present with bases 11 and higher. However, our findings of Benford's law and other bases demonstrate that if you have a large enough dataset that followed Benford's law in base 10, it will also follow Benford's law in bases 2 through 9.